Welcome back, everybody. Today we are continuing our discussion of light. Last time we talked a bit about polarization, and we're really getting into the nitty-gritties of what sort of deformation is occurring in the filaments that we hypothesize connect atoms to one another, which are essentially just the extensions of their own surfaces, their own electron shells.
And we're also, in addition to talking about the shape of the photon, I think today what we're going to focus on is we're going to focus on the relay events and how those relay events give you diffraction patterns. And so that's when you take a light, you shine it onto a gap, and then you get a interference, you get a pattern of light, dark, light, dark, light, dark on the photodetector that's on the other side of it.
Yeah, so why don't we just go ahead and take a look at that thing really quick. So this is essentially our classic diffraction pattern. And what you can see here is just what Anastasio was explaining, that instead of the light just producing a geometric circular, or I guess in this case a square pattern, it seems that the light is actually being somehow reflected in a banded pattern into the shadow region. So the geometric shadow does not actually occur. And what actually happens...
What do you mean by geometric shadow? Let's clarify
So
that.
the geometric shadow, right, if our slit was shaped like a circle, then we would expect that there would be a circle as a pattern that appears on the screen, and then there would be a circular shadow around it.
Sure, but we have a slit, and we do have, like, bands, which does seem
Yeah.
geometrically aligned, right?
So in a circle, you also have bands, which is really crazy and interesting.
Okay, so the slit doesn't have to be a slit. It could just be a gap.
No,
of
and
any
what's
kind.
actually, I didn't even totally want to get into this, but if you don't actually even have to have a slit, right? So you could just take a little piece of, like, you could stretch a hair across a laser pointer and get a diffraction pattern. And I think that's actually critical to what we're trying to bring to the table here, which is that it seems like there's an interaction between not only the atoms at the emitter and the atoms at the detector, but there's an interaction occurring along the way. And so the question becomes how to explain the casting of these bands into the dark region. And this really requires us to start to think about what kind of deformation of the filaments is happening during light. What are the pressures that are being put upon the atoms at the slit, at the borders of the slit, with respect to the atoms at the back with the detector? And what we've been moving towards is an idea that light has a sort of periodic push to it. It has a momentum, which has an angular quality to it, but that momentum seems to be pulsed. That means that there is periodic pushes and relaxations occurring along the tension filaments in between atoms. And so what we have in the picture here is an interesting case where some of these photon events, these light events, are relay events, in that they're traveling from the emitter to the edge where the slit is at, to the back. But some of the events are direct. So the interaction is merely occurring between the emitter and the detector.
The events that we're talking about here, if you're looking at the diagram, can be found at the edges of the slit, and these are relay events, right? Because the incident light that is coming from the emitter is going to hit against the side of the
slit.
the sides of
It's the diffraction surface.
That's what I was going to say. The diffraction surface or the sides of the slit. But then you're going to have some of the light that's coming through that is not touching anything necessarily on the slit. And so what's going on?
So what's going on here requires us to do a little bit of geometry and consider that these pulses of push, I don't want to say pull, but perhaps that's a reasonable way of thinking about it, that if light is pulsed phases, and phases is a really important concept here, of push and relaxation, that the timing at which those relayed pulses are arriving at the back screen once they're interacting with the slit is different than the timing of the ones that are arriving directly. And this is just due to pure triangular geometry, right? It's a longer path that must be followed in the relay event than the one that's occurring directly. And so the very simple explanation that we're proposing here is that those phases of push and pull get out of whack with one another when you have different distances to travel, as you do as that angle, this angle, let me point here, is increasing from here to here. And you have places where the phase of push on the detector is actually summing. And then as the angle increases, again, you have phases where they're summing to be out of phase with one another. And the result of this is simply that the atoms which are out of phase are becoming frustrated. They're getting essentially tugged on while they're, or pulled on or relaxed, while they're also being excited by a push signal from a different phase. And so the resulting interference pattern is essentially telling us the phase relationship between the atoms at the detector and the atoms that they have either interacted with or not interacted with along their journey.
And so my question, okay, so basically the idea is that if you're looking at this drawing, the center band on the detector is going to be the biggest band because the light is arriving in a way that is phase coherent. The light that's going through the slit and not interacting with anything is arriving at the same time as the light that is being emitted or relayed by the atoms on the sides of the slit because it's all in one direction. And so you get this maximal large peak at the center, at the back of the detector. And from this, you travel outwards in either direction, and as you travel outwards in either direction, you start to get progressively less and less light, which has to do with the angle at which things are being relayed from the slit over here. You can imagine that as your angle becomes more and more extreme, you're just going to get less light that's going out in that direction. My question is like a pretty basic geometric one, which is, why is it reflecting or relaying at such extreme angles in the first place? Because like if you look at this diagram, the light that's coming in is coming in all parallel to itself, and then there's just this like magical thing that happens in the middle of the slit where it just like goes off in this direction.
Right, so it's extremely important in these experiments that you have something with very at the edge, as even a human hair would do, at the very edge of it, there's only actually an atom, a line of atoms there. And at any really sharp blade, and in fact, you get these diffraction patterns best when you have a really sharp edge blade, because at the edge of a material object, you have an atom which is filamentary spread out in all directions. And it has the ability to relay at great angles because of that.
But when we talked about this yesterday and we were talking about the way that the angular momentum of the incident light is going to affect the relay angle of what's coming out of the atom, and you're shining something that's like a laser, which is a coherent light, then why would the atoms that are getting a coherent push of light, that it has that forward linear momentum, why would it suddenly make a turn for, 45 degrees?
Well, see that slit is receiving it's curved at the edge essentially, right?
So what you're saying is that like it's not really one atom, it's multiple atoms, and the majority of the atoms are going to transmit forward, and then the atoms as they follow the curvature of the object.
I think that's a better way of putting it.
Okay,
yeah.
That makes more sense.
Yeah.
Okay.
So.
And, hold on. Last thing. What I mean, like this, path of the light that goes through the center, which is deflected. Why is it deflected if it's not touching anything on the slit?
Well, I see. Because this slit is not a two-dimensional entity, right? It has a depth to it as well, right? So the slit has a depth to it, and
so you're basically saying that the center one is hitting against the top of the slit, and then it's going over here.
Well, against the back of it or something like that. Yeah. Okay, so the basic idea here that's really important to understand is that every atom during light is receiving a push which has a phase to it, of which it's maximally intense. And so along the filaments, there is a particular way in which this pressure is delivered, which happens to have angular momentum and stuff. And though that's important for other pieces of the discussion, for this discussion, it's just important to understand that the frequency of that push can get out of phase, especially when you have different lengths of distances to travel. And that's what leads us to develop these dark interference patterns where the atoms at the detector are actually being frustrated. They're not actually able to experience the full heft of the light as a result of those two conflicting signals that it's getting from the atoms, which are at different distances as a result of the geometry of the experiment.
Because to go back to the image, they're fundamentally showing a similar interpretation here, because what they're saying is that the darkness at the detector, like if you look at this node in the detector, is a result of the phase shift of the waves, right? So there's a phase shift. This is this delta here. And that is what is accounting for the darkness. And so it's not really a different interpretation, except for the fact that this middle wave is the wave that is not, it doesn't have a material basis for why it's shifting like that. It's, right, it's just this thing that's being channeled by the slit in the detector. And what we're saying is that there's actually a physical thing that's causing it to move.
Yeah, and I'm glad you brought that up. This isn't a particularly revelatory interpretation in and of itself. However, the idea that the atoms are being frustrated due to a material out-of-phase tug is a bit different than what you'll read about. And it's going to lead us, especially when we combine this for the threshold model of detectors, it's going to lead us to reconcile the Copenhagen interpretation, which is extremely important. And I think that's where we'll probably pick up with our next video, because the Copenhagen interpretation opened the door to all sorts of wild, superstitious business being introduced into physics, and the idea that things don't have to make sense.
Because, and you can see this already in the diagram, because the basis of this interference relationship is not the activity of the atom that is at the emitter and the activity of the atom that is at the detector. It is the fact that these photon waves become out of sync. And it is the difference between treating the photon as the object of interest rather than the atoms that produce the activity that is the photon, which is the basis of how the material world is different from the Copenhagen interpretation. But we'll talk about that next time.
Absolutely. And to complicate things worse, if this is as far as the story went, perhaps we would have actually arrived at a material explanation, because wave mechanics are generally an understandable material process. However, it seems like these interactions still behaved as particles in the initial experiments and today, right? You can still get these diffraction patterns even if you shoot them one at a time. And so we'll unpack that with the Copenhagen God, I can't say that freaking word. The Copenhagen interpretation next time.
Copenhagen integration next time. We'll see you soon.
See you guys.